American mathematician Harold Edwards wrote the book Fermat's Last Theorem, A Genetic Introduction to Algebraic Number Theory, where he provides a procedure for finding the decomposition of a prime number of a form 4k plus 1 with the aid of Fermat's real theorem, a chain of congruences, and Brahmagupta's identity. The basic idea is finding a sum of two squares, x squared plus y squared, that is divisible by the chosen prime number p, and then multiply that sum by its other divisor q, which must also be a sum of two squares, w squared plus z squared. The product of them, p times q squared, will have its squares divisible by the divisor q in one of the signed combinations, as the chosen prime number p has a unique representation as sum of two squares. This principle is best illustrated through an example. We choose 53 as the prime number. We find through Fermat's real theorem that 53 divides 2 raised to 53 minus 1 minus 1. Factoring it, we find that 2 raised to 26 plus 1 is indeed divisible by 53. So here we have an initial sum of two squares to work with. Next, we see that 2 raised to 26 plus 1 is the same to say 8,192 squared plus 1. And 8,192 is equal to 154 times 53 plus 30. That leads us to notice that 53 must divide 30 squared plus 1. Actually, 30 squared plus 1 is equal to 53 times 17. And given that it's easy to find that 17 is 4 squared plus 1, then we can multiply both sum of two squares, as that will have 17 twice as a factor, and so dividing both squares with one of the signed choices. As you see, it divides 119 and 34. So we finally find that 53 equals 7 squared plus 2 squared, the solution we sought. Well, the case for prime 53 was swiftly solved because 17 is easily decomposed as 4 squared plus 1. Edwards' general solution is to start with known equation p times q equals x squared plus y squared and derive from it another sum of two squares, q times r equals w squared plus z squared, where p times q is bigger than q times r. The product of them is p times r times q squared, and so have q twice. And that product is a sum of two squares, if you remember the Brahmagupta's identity. And so q divides both squares in one of the signed choices. After dividing by q, we get another sum of two squares, p times r equals x sub 1 squared plus y sub 1 squared. That is smaller than the initial one, thus kickstarting a descent. That lays down the short descent framework needed to find the decomposition of a prime number as sum of two squares. Edwards' clever move was to provide a procedure for deriving q times r equals w squared plus z squared, once you already got p times q equals x squared plus y squared. So we set x equals n times q plus minus w, and y equals m times q plus minus z, where both w and z are smaller than q. Next, we apply those equations to Brahmagupta's identity. There, we see that in the second square, we have w times z twice. So the trick is to find the proper combinations of signs so that they cancel each other. By doing so, we will have the second square divisible by q. Furthermore, in the first square we can regroup terms, so that the first one is also divisible by q. Then, in the second bracket, we got a sum of two squares, w squared plus z squared. As q divides all the other terms at the left and right side of the equal sign, then it must also divide this sum of two squares. And so, we can divide both squares by q, and thus find p times r, which is a smaller sum of two squares. So let's see how this applies to prime 53, the same case seen before. This example pretty much explains itself. So press pause and check it out. As a first conclusion, Edward provides a smart solution to the problem. Yet, you have to pick the appropriate linear forms of the squares to effectively arrive at the solution. Otherwise, there wouldn't be a short descent but a longer one. For small primes, picking those forms are usually trivial. Other times, not that easy. Let's have a look at the case prime 53, where we chose 4 and 16 as the residues modulus 17 for 30 and 1. That worked quite well, but had we instead chosen other forms for 30 and 1, then we wouldn't have reached the final result that fast. Here, we can observe the outcomes when alternative forms are chosen for 30 and 1. The bad news is that Edward's short descent method hits a roadblock with some numbers. Next, we'll see prime 797 as a counterexample. Fermat's little theorem gives us an initial equation. Setting 215 and 1 in forms that minimize the residues modulus 58 gives this. So as we derived earlier, the sum of the squares of the residues is divisible by 58. So we have that 41 square plus 57 square equals 58 times 85. But we see that 85 is bigger than 58, which means we are not getting the descent we want. We can try another setting. This time 215 equals 58 times 4 minus 17. There we have 17 square plus 57 square equals 58 times 61. Here again, 61 is bigger than 58, so we don't have a descent either. Somewhat might say, hey, why not start with 582 square plus 1, since 797 minus 215 equals 582? But that leads us to the same kind of solutions. No descent in sight. Believe me, or better, try it for yourself. Spoiler, there's no descent either. Here's the crucial point. For a successful descent, minimizing the residues is essential. Turns out A has to be 3 or 4 to make that happen. But those values just give us what we already found. Bottom line, Edward's short descent method proves inadequate when dealing with primes such as 797. To make it work, we've got to tweak the algorithm a bit. So the little change is finding forms where d is equal to b squared. That means that b squared plus 1 is 58 times c. So c must also be a sum of two squares. And we must find a value of c that is smaller than 58 to ensure a descent. Next, we solve for b in the first equation and insert that in the second. So we get this equation. And in order to minimize c, we see that a needs to be close to 4. And when a is 4, then we find that c turns out to be 5. So the sum of the squares of the residue is this. Sure, 17 squared times 5 is bigger than 58, but that vanishes in the next step. Once we got this, we apply the Brahmagupta's identity. In this step, we see that not only 17 cubed is simplified in the second square, but in the first square, 58 times 17 squared times 5 is also simplified. And so we can now simplify both 58 squared and 17 squared. We end up with a smaller equation. 797 times 5 equals 4 squared plus 63 squared. As 5 is easily decomposed as 2 squared plus 1, then we apply Brahmagupta's identity again. And we can divide all terms by 5 squared, thus reaching the solution. 797 equals 26 squared plus 11 squared. Although this may seem messy, there's a convenient shortcut available. We can begin with our earlier derivation, just keeping in mind that while C may indeed be a prime number, it could also be composite. Therefore, it's crucial to consider the prime factors of C. Applying Brahma-Gupta's identity, we eventually reach this solution. We should provide some context on how we reach the equation highlighted in gray. The derivation of this equation is presented below, making it easy to understand the steps involved. If C is not a prime number, but a composite one, then that will be our first descent, and we'll have to do again this protocol for the prime factors of C. So, in a second descent, we'll finally get another equation that is smaller. In this example, we assume here that C has only two prime factors, C sub 1 and C sub 2. Finally, we apply Brahma-Gupta's identity again with the equations obtained in descents 1 and 2. And so, all terms can be divided by C sub 1 squared. Thus, we reach a smaller sum of 2 squares. We then have to repeat the procedure for C sub 2 and gamma, and we'll eventually find the desired solution. Let's consider an example to illustrate and compare both methods. Take the prime number 12,601, for instance. We observe that the little tweak method swiftly resolves the problem, whereas Edwards' procedure entails numerous steps, prolonging the process considerably. Press pause here to go through the explanation. However, it's worth noting that despite its efficiency in certain cases, the little tweak method doesn't consistently outpace Edwards' procedure. Even when Edwards' method exhibits no immediate descent, the little tweak doesn't always prove to be faster. Bottom line, many times the little tweak doesn't really give us an edge over Edwards' method. So figuring out the solution turns into a more hands-on case-by-case thing. See here case prime 12,569, derived first with Edwards' method and then with the little tweak. The efficiency of the methods depends mostly on the prime factors involved in each step. Before going to the conclusions, let's check how the little tweak works with a big prime number, a 10 digits number. Pause and check for yourself. As an overall conclusion, Edwards' short descent nails the problem. It does provide a smart solution. However, it's worth noting that neither his approach nor the little tweak provide a fast solution on all situations. You've got to handle each case differently, maybe even combine both methods if necessary. So our question arises, are these the infinite descents that Fermat discovered? Or did he develop a totally different procedure? Well, in the next sections, we'll see a variety of infinite descents.